Hi, so the second video I want to deal with states of matter, and that's changing states of matter like solids changing to liquids, liquids changing to gases, etc. So let me get a diagram up. Right, so following on from the first lesson, these are particles arranged in a solid, these are particles arranged in a liquid, and clearly these are particles arranged in a gas. And if you heat a solid, you can melt it and it will turn into a liquid. If you heat a liquid, you can boil it and it will turn into a gas. The temperature at which the solid turns to liquid is called the melting temperature, or the melting point. The temperature at which a liquid will boil and turn into a gas is the boiling point, or the boiling temperature. And I'm going to be talking about melting points and boiling points today, but equally at the same time, what temperature does the opposite of those things happen? For example, if I've got a gas and I cool it, I cool the gas back into liquid, what temperature will the gas cool back into liquid? And it will cool back into liquid at exactly the same temperature that it would boil from a liquid into a gas. And so the boiling temperature, the boiling point, will be the same point, the temperature at which something will do the exact opposite, that is go from gas back to being a liquid when it's cooled. Equally, melting point, melting temperature will be exactly the same temperature at which the liquid will freeze, the freezing temperature, freezing point. People tend not to call these freezing points or condensing points, they tend to call them melting points and boiling points, and as scientists we know that the opposites are exactly the same temperature. You have to heat solids to turn them into liquids, and you have to heat liquids to turn them into gases. Going the other way, you have to cool them. Sometimes I use the phrase cold it. So to cool the gas, cool it back into liquid, cool the liquid, cool it back into solid, or cold the liquid, make it colder, and it will at some very cold temperature turn to solid. Now you've got this strange thing that happens with a few common chemicals. You will have them go straight from being a solid to a gas. The most famous one of these is solid carbon dioxide. Solid carbon dioxide, if you warm it, goes to give you gas carbon dioxide. It does not give you liquid carbon dioxide first. So with solid carbon dioxide, which we call dry ice, you can't kind of melt it to make a liquid. It goes straight from a solid to a gas. It sublimes. That is called sublimation. And the opposite of sublimation, when you've got gas and you cool it, like say we had carbon dioxide and we cooled it down, it would go straight to a solid, and it would happen at the same temperature, and we would call that the reverse of sublimation, believe it or not, called reverse sublimation. So it hasn't got a posh name, we just call it reverse sublimation. All of these changes you need to be able to name, and the one that people forget about is this one. The gas back into liquid is called condensing. You could talk about water vapor that's in the air hitting a cold window, making droplets of water, condensing. That's condensation of water. But condensing as a term is any gas being cooled, making the liquid form of that gas. People use this word wrong, boiling. Boiling happens at the boiling point. Some people want to call that evaporating. Evaporating is where the liquid particles turn into gas particles, but that happens at any temperature. It does not happen at one temperature. So there are differences in the words boiling and evaporating. At the moment, I'm talking about boiling. I'm talking about the one temperature where the particles of a liquid turn into particles of a gas. Now let's get into a little bit more detail. Let's try and get our mind around what is actually going on. And what's actually going on, if I try and mimic the behaviour with my fist to try and make you think about it. Say you've got a solid. Say you take ice out of our freezer. It'll be like minus 20 degrees. And put it in the room, it'll warm up. The particles are vibrating. They're doing this in their places. As the temperature of the ice warms up, then the particles are vibrating more and more and more and more. As the temperature gets to 0 degrees, at 0 degrees, then the vibrations are so big that the particles break free. They break free of that regular orderly structure. And then at 0 degrees, they start moving around each other. That is melting. Melting is when they break out of their arrangement. So the attractions, there are attractions here between the particles. There are attractions there. The attraction there have kind of been loosened. You have to loosen the attractions of a solid in order to turn it into a liquid. And the temperature which that happens, that's melting, or the melting point. When you've got, say, liquid water, the ice has melted, you've got water, and then you warm it up, say you put a Bunsen burner underneath. I want you to picture that the particles are moving around each other at 0 degrees, and then you warm it up and the temperature goes up to, I don't know, 5, 10, 15, 20, 30, 40, 50, 60. The particles move around faster and faster and faster and faster and faster and faster until 100 degrees water. The particles break free completely of each other's attractions. When they break free of each other's attractions, then you get gas made. Then the particles are free to go in whatever direction they want, and they'll be moving pretty quickly at that point. The temperature at which that happens, we call it boiling. Now, if you look at the body of a liquid, you've got a beaker. Look in the centre of the beaker. When it's boiling, you get bubbles, you get gas made inside the liquid body. When there are gas particles made inside the liquid body, then it's boiling. It's not boiling until it reaches 100 degrees. Before that, there may be some water vapour coming off. That's evaporating. Evaporation will happen at 1 degree, 2 degrees, 3. Evaporation will happen at any temperature that you've got water. So liquids will evaporate. The odd particle will shoot out of the liquid, and that's evaporation. Those particles that are shooting out are always coming from the surface of the liquid. That's not boiling. Boiling only happens at the boiling point. With water happens at 100 degrees. Now, picture a liquid. The particles are doing this. And picture a gas. Picture a gas. The particles are zipping around all over the place, moving really, really quickly. What happens to their motion if you could get them even hotter? Even hotter would mean that the particle would move around even faster. They would move faster and faster and faster. There's no upper limit. The more the temperature, the more the particle will move. For those who are interested, there's an interesting equation which in science says that the temperature of anything is directly proportional to the average kinetic energy of the particles that are making it up. So if the temperature goes more and more and more and more, the particles' average kinetic energy will get more and more and more and more and more, and the only way you can do that is to move around faster and faster and faster and faster and faster. If you cool it down, the opposite happens. If you cool gases down, they slow down until the attractions make them such that they move around each other. And then when you cool a liquid down, the movement gets slower and slower and slower until they stop moving around and make a pattern and vibrate. That's a solid. And then the vibrations, if you cool a solid down further, the particles will get vibrations, will become smaller and smaller and smaller. On that equation I was talking about, the average kinetic energy is the temperature. Then when does the movement actually stop? Well, the particles of a solid are vibrating. The vibration will get smaller and smaller until they will stop vibrating at 0 degrees Kelvin. That's minus 273 degrees Celsius. That's called absolute zero. It was Kelvin that came up with the idea that why do we start the Celsius scale at 0 when there are colder temperatures? Why don't we start measuring temperature at the coldest possible temperature? The coldest possible temperature is absolute zero. So on Kelvin scale, absolute zero is 0, and normal 0 degrees Celsius on the Kelvin scale is 273 degrees Kelvin. We don't say degrees when we're talking about Kelvin scale, we just say 273 Kelvin. So, anyway, sorry, back to GCSE. That Kelvin discussion is more A level. But back to this GCSE, I want you to be able to name these changes of state. Name them, even the sublimation and even the reverse sublimation. And I want you to know that there's a temperature at which something will melt. There's a temperature at which something will boil. And you can look up the melting temperature and you can look up the boiling temperature that any pure substance has. Water, for example, melting temperature is 0, boiling temperature is 100 degrees Celsius. Now, there's only one chemical in the world that will have exactly 0 degrees Celsius melting temperature and 100 degrees Celsius boiling temperature, and that is water. Anything that does that has to be water. So, melting temperatures, boiling temperatures, we can use them to identify chemicals. If you don't know what chemical you've got, do its melting point, do its boiling point, look up the melting and boiling points of chemicals, and you can often identify it. So, next I'd like to go through how these change on a graph. How does the temperature change on a graph? So, let's, I've written some points there. If you want to pause that and go through that, I don't particularly want to stand here and read that. But I would have said to you those things when I was giving my opening blurb. Right, this is what I want. I talked to you about getting ice out of a freezer. Let's talk about that. That temperature there being, say, minus 20 degrees. If you leave ice out, it'll get warmer and warmer and warmer and warmer. And at that temperature, 0 degrees, it will start to melt. Now, as it melts, it will stay at 0 degrees. The temperature will not rise above 0 degrees. The 0 degrees melting temperature will be constant while you've got a mixture of the solid and the liquid states. So the ice is melting. This is time. The ice takes that long to melt. It's melting, 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 melting. When you get to that temperature, it's now melted. Now it's all liquid. Now it's all water. Then the temperature of water will then start to rise up. The temperature of the water, if you warm it, will get higher and higher and higher and higher until it reaches this point. And that point is the boiling point. And when water boils, the temperature will remain at 100 degrees. It'll be boiling, 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 and there it's all boiled. If you keep the gas, water, gas, steam, keep the steam separate and warm up the steam and heat up the steam, then you get higher and higher and higher and higher temperatures that go on and on and on and on and on. The important thing of this is you've got to know melting points and boiling points, melting temperatures, boiling temperatures, and we can identify unknown chemicals from those, from that data of what temperatures are the melting point and boiling point. GCSE requires you to know that. It requires you to know that the temperatures stay constant when something is melting or boiling. Next, I want to deal with impurities. How do impurities affect the melting and boiling points? So, the temperatures we see on the internet, that we can download for various chemicals, melting points, boiling points, are for the pure chemical. Well, impurities affect that temperature, and I'm going to talk about that in a minute. But the other thing that affects that temperature is the pressure. Now, all of these things we measure under normal atmospheric pressure at sea level. If you go up to a lower pressure like top of Mount Everest or top of K2, the second highest mountain in the world in Pakistan, then the pressure up there is much lower. If the pressure is lower, the boiling points are different. Water boils at something like 70 something degrees. By 80 degrees it will all boil away because the pressure is less up there. So these temperatures are quoted under 1 atmosphere pressure, and they're quoted as the pure chemical. Well, what about the impure chemicals? Well, the impure chemicals affect the melting points and boiling points. The first effect they have is that if you've got an impure chemical, let me just turn this off. If you've got an impure chemical, like the chemical we're talking about, mixed with an impurity, then it won't melt and boil at one exact temperature. It will melt and boil over a range. So for ice, for example, say we make ice cubes made of salty water, salt being the impurity, the water being the chemical we're talking about. Then ice cubes made from salty water will melt, say they will melt between -5 degrees and -2 degrees. So there's a range, there's a 3-degree range over which they will melt. So impurities give you a range, not just for melting temperatures, but what about boiling temperatures? Well, again, say we've got salty water. Salty water will boil, for example, depending upon how much salt you've got, this is just typically from 102 degrees to 106 degrees. That boiling point range you'll have instead of one exact boiling point. So impurities give you a range. They don't give you one temperature. But then there's one final thing you need to know, is if you looked and listened to the values I picked, the melting temperatures with impurities tend to go down and the boiling temperatures tend to go up from where they would be had it been pure. So boiling temperatures are elevated, melting temperatures are depressed. But we get ranges with things that are not pure. So say for example, you are in an exam and they ask you to predict melting temperatures, boiling temperatures, then I ask you to think about these points. Hopefully my thing will come up. No. Right, sorry, I can't seem to get my projector to display the final slide. But I asked you to think about melting temperature will go down, boiling temperature will go up, impurities will also give you a range. So we often know how, if there's a lot of impurities, the range is bigger. And the elevation of boiling point, depression freezing point is more. If you've just got a little bit of impurity, then the deviations from the one boiling temperature, one melting temperature are a lot less. Okay, I'm going to stop there because I think I've been whittering on for long enough, and I'll carry on next time with how do we know we've got these particles? How do you know that Ahmed just hasn't been going off on teaching you a load of gibberish nonsense? Well, we'll do that next time. Take care.